Okie dokie chemists, let's get started. All right, so the plan is for today is to just finish this first part of chapter 16, only the concepts that are on midterm 2, which is tomorrow in recitation. So there's like 15 or so slides that we have to get to that will be covered, and then we'll have a small break. Then we'll go directly into midterm 2 review, and whatever time remaining, I'll finish up my office hours if you have specific questions about anything. Hopefully my demo comes into the secret window so I can do a demo at the end of this lecture content. All right, so we left off talking about acids and bases. We talked about acids and bases a little bit in chemistry 1210, but really it was just neutralization reactions, stoichiometry, that kind of stuff. So now we're going to dive deeper into the idea of weak acids and weak bases in this chapter and explain pH values. And so this slide is what I call the magic square that allows us to convert between our pH scales and what they represent. So remember, H+ concentration and hydroxide concentrations in water are very, very small. And so those really small numbers are better represented with a logarithm scale. So if you know the concentration of H+ at equilibrium in your solution, to convert to a pH value, you just take the negative log of that H+ value. Same thing with OH-. If you know the OH- concentration at equilibrium, if you take the negative log of that number, so negative log hydroxide concentration, you get the POH. So P is just a function. It just means negative log of that thing. So pH is negative log H+, POH is negative log OH-, P bananas is negative log concentration of bananas, etc. So all water aqueous samples have a set amount of H+ and hydroxide, where the product of those two values always equal to the Kw, so big K, of water at that temperature. So 99% of the time in this class, we are going to be working at 25 degrees Celsius. So that means that Kw at this temperature is 1 × 10 to the -14. And so that Kw expression comes from the self-ionization of water, which I talked about in this previous slide. Let me just go up real quick. All right, so this is the self-ionization of water. It has its own K value, where a water molecule basically splits up into an H+ and hydroxide. So here is our K expression for the self-ionization or auto-ionization of water. Kw is H+ concentration times hydroxide concentration. So that's what I meant by the product of these two numbers. So we can make a direct relationship if you know one of those values. If you know H+ concentration, you actually also know hydroxide concentration as well, because Kw is equal to H+ concentration times hydroxide concentration, and that is always equal to a constant. In this case, at 25 degrees, is 1 × 10 to the -14. Right, so we're filling in this square. So what we get here is, okay, you can take the negative log of H+ to get pH, negative log of hydroxide to get POH. These two P values, so pH and POH, are related to one another by the relationship pH plus POH equals 14. And where that 14 comes from, that 14 is actually negative log of Kw. So Kw is 1 × 10 to the -14. Negative log of that number, 1 × 10 to the -14, is 14. So that is basically the magic square and how we can get the relationships of everything. If we wanted to undo a pH value to go back to H+, we do 10 to the negative pH. That's how we go back to a H+ concentration. So if I tell you, you have a solution, it has a pH of 4, then that means that the H+ concentration is 1 × 10 to the -4. Same thing with POH. If you want to undo that POH value, you do 10 to the negative POH. All right, so this is a very important concept. The reason I call it the magic square is because if you just know one corner of this square, just one corner. You actually know every single variable within it. If I give you the H plus concentration, you can tell me pH, you can tell me POH, you can tell me hydroxide concentration. If I give you hydroxide concentration, you can fill in the rest of the square. You know all 4 quadrants as long as you know one of those values because of the relationship between KW. All right, so that's how you navigate that square for an aqueous solution where we're talking about acids and bases. Okay, so we'll use that in calculating pHs of various solutions. So in this chapter, we're going to look at calculating the pHs of strong acids and bases and weak acids and bases. But for midterm 2, we are just going to assess you on strong acids for now. So weak acids and bases and those pH calculations will come later. They're a little bit more complex. So we'll just focus on strong acids and strong bases. And so the big idea for calculating the pH of a strong acid or strong base is that these substances are strong electrolytes, meaning they fully ionize when you dissolve them in solution. So remember, it's the H plus that gives us our pH value, or it's the hydroxide that gives us our POH value. So if you drop HCl into water, this is a strong acid, so it doesn't exist as HCl in solution. No, it actually exists as H plus and chloride minus floating around in solution. So this fully ionizes when you drop a strong acid into solution. So that means if I tell you, okay, you have an HCl concentration and it's 1 molarity, that means the H plus concentration at equilibrium is also 1 molarity because it fully ionizes. That's the assumption we're going to make with strong acids and strong bases, that these things fully ionize, right? And then we're just one step away from calculating the pH. All right, so that's a strong acid like HCl versus sodium hydroxide here. Same, but it's the same idea. Sodium hydroxide, this is like a salt, it's like NaCl. It doesn't exist as NaOH bound together when you dissolve it in water. No, it separates into its cations and anions. So you drop sodium hydroxide in water, you get 1 equivalence of sodium plus and 1 equivalence of hydroxide. Those hydroxides fully ionize, and that's what's going to give us our pH values that will come a little later. So if I tell you that you have a solution and it's 1 molarity sodium hydroxide, what would be the concentration of hydroxide at equilibrium for that solution? 1 molarity, perfect. But what if I told you you had calcium hydroxide? That was 1 molarity. How much hydroxide? What's the concentration of hydroxide in that solution? Is it also 1 molarity? It is 2 molarity. Yes, it's 2 molarity. That one's a little bit different, and it's just because calcium hydroxide has 2 hydroxides per, one unit. All right, so that's the only difference. All right, so those are strong acids and strong bases. Just know that these things fully ionize into solution into those cations and anions. We'll talk about this a little bit later on Friday about weak acids and weak bases. It's the same idea. Weak acids produce a little bit of H plus in solution. Weak bases produce a little bit of hydroxide in solution, but they don't fully ionize. They actually have K values that we will inspect a little bit further. We'll have to do ice tables. So you can see here in this picture, this is a weak electrolyte because if you look closely here, it's not fully ionized. There are some intact particles still there, but some ions as well. And the extent that this happens is dictated by the magnitude of those Ks. But again, we'll talk about that later. We'll focus on strong acids and strong bases. Okay, so let's calculate some pHs and POHs for strong acids and strong bases. I will guarantee you a question like this will show up on your exam, where we're assuming all of this is at 25 degrees Celsius, and this is important. That clarification is important because that means Kw equals 1 times 10 to the negative 14. And so that means we are allowed to do pH plus POH equals 14. All right, so that's an important little concept, detail there if I tell you that this is at 25 degrees Celsius. So what is the pH of a 0.025 molarity HCl solution? So HCl is a strong acid, so we're going to assume it fully ionizes. We're assuming that the HCl concentration is the same as the H plus concentration. So given this information, we can say, okay, the H plus concentration at equilibrium is coming from that strong acid. It's 0.0250 molarity. So to calculate the pH, we simply just take the negative log of the H plus value we just got. So negative log 0.0250 molarity, and that equals something, it's in the corner written there, 1.602. And so let's remember our sig fig rules for logarithms. The number of decimal places, or sorry, the number of sig figs in our molarity value is equal to the number of decimal places in our pH value. That 1 doesn't count towards sig figs. That 1 is telling us the magnitude of the number, while all of the decimal places after the pH is giving us the sig fig values. So you might want to write like 1.60, but that's technically not right. We have to put 3 decimal places after that 1. So there we go, a pH of 1.602, and that is well in the acidic region, and that should make sense because we put an acid into water, so it should be acidic. All right, so let's do another one. What is the pH of a sodium hydroxide solution? So again, this is a strong base. We're going to make the assumption that that strong base fully ionizes because it's a strong electrolyte. We're going to assume that the hydroxide concentration of this solution is 0.0175 molarity. All right, that's fully ionizes. And so to calculate, we can't calculate pH directly. We are actually going to calculate pOH first because we have a concentration of hydroxide. We don't have a concentration of H plus right away. So I'm going to do negative log of that hydroxide number, so 0.0175 molarity. I didn't calculate what that is, negative log 0.0175. And so I get that this is 1.757, but is that number my pH? Is not, it is my pOH. So I need to do one little extra step, all right? That's my pOH. I need to do 14 minus that pOH to get me my pH. So I'm gonna subtract that number from 14 and get that my actual pH is 12.243, all right? And that number hopefully is a little bit more satisfying because a pH of 12 is well in the basic regime above a pH of 7, so it's definitely basic. You know, asking small questions like that will be really helpful. Ask yourself, what did you put into water? We put sodium hydroxide into water. Sodium hydroxide's a base, so the solution should become basic. So, but you know that if this was a multiple choice question, I would put 12.24 and 1.75 because that's a common mistake. A student might not subtract it from 14. But if you wanted to say, oh, you put sodium hydroxide, a base, into solution and the solution became 1.7 acidic, hopefully something in your mind says, oh, that doesn't make sense, and you know, maybe I'm missing a step. So always ask yourself, what are you putting into water, an acid or base, and make sure that it matches your answer. Okay, so last one here, what is the pH of a calcium hydroxide solution? So in this one, it's a little bit different because calcium hydroxide has 2 hydroxides in it. So we can't just shove that number into our pOH calculation. If my calcium hydroxide concentration is 0.003, that means my hydroxide concentration at equilibrium is actually 0.0060 molarity because of those 2 hydroxides. So that's a small little detail, right? That there's twice the concentration of those hydroxides for the calcium hydroxide formula unit. So this one's very similar. We're going to calculate pOH first, then subtract from 14 to get pH. So our pOH is equal to negative log 0.0060 molarity. And so if you calculate that, you get something like negative log 0.006, 2.22. And so note here, there are 2 sig figs in that concentration. So I have 2 decimal places in my POH. And this is in fact POH. It's not my answer. We want to express this in pH. So you're going to subtract that from 14 to get your pH. So I have that in the corner. It's 11.78. And again, that number matches, you put a base into water, it should be basic. It shouldn't be acidic. All right. So those are basically your strong acid, strong base calculations. They're not that bad. So let's get a little bit more complicated and throw some other concepts in here like saturated solutions and dilutions, because those are skills you should already have from Chem 1210 or from our saturated chapter in chapter 13. And we can calculate the pHs of those solutions as well, because all we really need is concentration of H+ or hydroxide. So let's figure what that is with some manipulation. So in this first one, you throw a large scoop of barium hydroxide into water, but not all the solid dissolves. So to me, like in chapter 13, this sounds like a saturated solution. All right, since you throw a huge chunk in, but not all of it dissolves. You look up in a textbook that barium hydroxide has a solubility of 0.1077 at this temperature. So let's calculate the concentration of hydroxide in the solution. So we're not counting the concentration of the solid at the bottom. We just want what's the concentration of the hydroxide that's actually dissolved in the solution. And so since I tell you that the solubility, the max solubility of barium hydroxide is this, it means that you have a concentration of 0.177 molarity in a saturated barium hydroxide solution. So we're not counting those undissolved solids at the bottom. We're just pointing out what is actually dissolved in that solution. So that means if the solubility of barium hydroxide is 0.1077, then the hydroxide concentration is just double that number, since barium hydroxide has 2. Note it has 2 hydroxides for every formula unit. So we can't just negative log the number as is. We actually want the hydroxide concentration. So this is 0.2154 molarity of hydroxide. All right. So I just doubled that number. And so to get the pH, we're going to do the POH calculation first and then subtract from 14, because this is at 25 degrees Celsius. So our POH is negative log 0.2154, and that is equal to, let's see, boop, boop, 0.66, how many sig figs? 4 decimal places, 6668. All right, but that's our POH. So to get our pH, we're going to do 14 minus that number we just got, so 0.6668. So that means our pH is closer to 13.3 something. So yes, that is in a basic regime, which should make sense since we put a base into water. This is a basic saturated solution. All right, so let's just do one more. So that was a saturated example and the pH. So let's take 1 liter of the saturated solution, so just the solution above it. We're not taking any of the dissolved solids. And we remove it, and then we add an additional 50 milliliters of water. What is the final pH of that solution? So right now we have a very basic solution. So this is what we have right now, the saturated barium hydroxide. They're solid at the bottom. The solution we just calculated has a concentration of 0.2154 molarity hydroxide concentration. So we're going to take 1 liter of that and mix it with 500 milliliters of water. So what we're essentially doing is diluting it, right? We're just diluting that hydroxide concentration. So this new volume that we have is not 1 liter, it's actually 1.5 liters, all right? So we want to figure out, okay, what is the concentration of hydroxide in this new second beaker? We know that the concentration of the original solution is 0.2154. We did that in the previous section. Now we want to figure out what is that new concentration. This is just simply a dilution. So we're going to do M1V1 equals M2V2. So M1V1, M2V2. So going through these numbers, so 1.5 liters is going to be V2. That's our new diluted volume. We are solving for M2. That's what we want to figure out. M1 is the original hydroxide concentration. So it's right there. It's what we're taking and diluting. So this number is M1. So then finally, what is the value of V1? It would be 1 liter, yeah, because we're taking 1 liter of that original solution and diluting it to 1.5 liters. So this number is V1, while V2 is the sum of those two numbers, all right? So now we're just going to hopefully get an M2 value that's diluted. The hydroxide concentration should be a little bit less. So we're going to do 0.2154 molarity of hydroxide. That's the original hydroxide solution. We had 1 liter of that, and we're going to dilute it to 1.5 liters. And we are solving for what is the new concentration of that diluted solution. So hopefully it should be a smaller number than it was before. So 0.2154 divided by 1.5, I get that the new concentration of the diluted solution, so M2, is equal to 0.1436 molarity, and this is of hydroxide. Because the number I put inside this M1V1 calculation is also hydroxide. All right, that's not our answer. We need to do our POH-pH calculation again. So if you do POH calculation, so negative log that number, you will get 0.84, 8428. And so if you subtract that from 14, you should get a pH value of 13.572. So we see that diluting this basic solution made it less basic. It didn't make it more acidic. It just made it less basic because there's a lesser concentration of hydroxide present. Right, so that's kind of like elevating these POH-pH calculations by incorporating dilutions or saturated solutions and manipulating those. Okay, let's do one more application of pH calculations. This one is about acids. So let's calculate the pH of a mixture this time that we form by mixing together 2 different acids. So we're going to mix together HCl and HI. Both of these are strong acids. All right? So each acid contributes a certain amount of H plus to this solution. So remember, a pH value is just related to the total amount of H plus that's present in that solution. We always made an assumption for like HCl. If you had a 1 molarity HCl solution, we just assumed that H plus was also 1 molarity. But in this example, now there's 2 sources of acid. So all we have to do is just calculate what is the total concentration of H plus present in this solution. So I want to calculate how much H plus is coming from, you know, this first HCl source, how much is coming from that one, and then how much H plus is coming from the other source, and then calculate the total concentration there. So I have kind of like a formula here where the concentration of H plus total in this mixture is equal to, again, the contribution of HCl and the contribution of HI over the total volume in liters here. I'm going to tell you a little tip here for that'll be helpful in chapters 16 and 17. We know that molarity is the unit moles per liter, but oftentimes working in liters is difficult because, you know, in lab and stuff, you're not measuring stuff in liters because a liter is a lot. Typically, we're measuring volumes in milliliters. So a tip here is that a milliliter times a molarity equals a millimole, right? So if you just don't convert, so notice that these are milliliters and these are molarities. If you just multiply these 2 numbers together, you will calculate a millimole amount of H plus. And you might be like, why work with a millimole? The reason, if you work with millimole and keep everything in milliliters, then a molarity will come out. So if you take that millimole and divide it by milliliters, you'll get a molarity back. And that's really useful because then we never have to, multiply and divide by 1,000 when we don't need to. So what we're going to see here is if we multiply these two numbers together, the milliliter amount and the molarity amount, so 50 times 0.02 is 1. So 1 millimole of H plus comes from that HCl source, right? The number 1 is a lot easier to work with than 0.001 moles, right? If we just stay in millimoles. And I promise you, when we get to chapter 17, you'll want to work in millimoles. Same thing for the second one. Just keep everything in milliliters and calculate a millimole. So 125 times 0.01, this is 1.25 millimoles of H plus. Right? Those numbers are a lot easier to work with than 0.001 and 0.00125. All right? So staying in millimoles is a lot easier than converting these to moles when we don't really have to. So you can clearly see that each of these acids are contributing a certain millimole amount of H plus. So if we calculate this H plus total down here, all right, 1 millimole of acid is coming from HCl. 1.25 millimoles of acid is coming from HI. And now we just want to divide by the total volume of the solution. But since we're working in millimoles, let's just make sure that this total volume is in milliliters, because a millimole divided by a milliliter is a molarity. And so what you see is we never had to convert to liters. We never had to multiply or divide by 1,000. So I'm going to introduce it now, and I'll show you again how useful it is in chapter 17. So what is the total volume of this mixture when we mix together this HCl and HI? 175. Perfect. Yes. And so we see that from the two sources, there's actually a total of 2.25 millimoles of HCl, or sorry, H plus total in this solution, because there's two sources. And so when you do that, you get 2.25 divided by 175. Boop. So I get that the total H plus concentration in this solution is 0.012, probably 3 sig, maybe 2, yeah, 2 sig figs, but I'll just add an extra one here. 0.0129 molarity of H plus. That's an important number because we need that to move on to the next step to calculate pH. So simply to calculate pH, we just negative log that number. So negative log 0.0129 molarity. Though in my calculator, I'm not going to rewrite the number. I'm just going to do negative log answer. I'm not going to round at all. Yeah, when the 9 is at the bottom, it just means it's not part of the sig figs. I just want it there. So I'm not pre-rounding, all right? And so what we get is that, yeah, the pH is 1.89. And that's good. We put acid in water. The pH should be acidic. Okay. So there's another application of mixing two acids. Both of them are strong, so you just need to get the total H plus concentration from those two sources. Okay. All right, one more. Okay, so we have a solution that has a KOH concentration of 0.01 molarity. What is the H plus concentration of this solution, but not at 25 degrees, at 50 degrees Celsius? So here I tell you the Kw of 50 degrees Celsius is a different number. It's not 1 times 10 to the negative 14, it's 1.1. Or sorry, it's 5.5 times 10 to the negative 14. So here, this is a multiple choice question because I'm trying to trick you into saying something like, you see here that we're putting a base into solution. KOH is a base. You can tell from the hydroxide that's present. So here, A is not going to be correct. I don't want you to say that a solution cannot have H plus present in it because it's a basic solution. Remember, water always has an equilibrium present, always. There's always some amount of H plus and some amount of OH minus present. Kw, which is equal to H plus concentration times OH minus concentration. This is an equilibrium that's always at play. There's always a little bit of H plus present. There's always a pH, there's always a POH present in a solution, but in this one it's just a little bit different because we're not at 25 degrees Celsius. So, all the strategy here is from this KOH concentration, we can deduce that the hydroxide concentration at equilibrium is also 0.10 molarity. And so together with the KW information, look, I give you KW. We just assume that the KOH concentration is the same as the hydroxide concentration. So we're just going to calculate what amount of H plus has to be present also in this solution for KW to be correct. All right, so we can't say A. There is a little bit of H plus. That's why even, basic solutions have a pH. They have a pH, but it's a large number because that pH is like, 12 or something because the H plus concentration is so small. So we are just going to do 5.5. So let me just rewrite this real quick. We're going to use the expression KW equals H plus times hydroxide concentration. We know this number. We know this number. We're solving for that number. All right. So 5.5 times 10 to the negative 14 equals that H plus concentration that we're solving for times 0.010 molarity, right? And so if you solve for that, we get that the H plus concentration is something like 5.5 times 10 to the negative 12. So I think it's this one. There we go, D. Right? So you can see in this basic solution, here is their concentration of hydroxide, here is your concentration of H plus. Yeah, there's just a ton more hydroxide present. And that's what the definition of a basic solution is, when there's more hydroxide than H plus. While an acidic solution is there more H plus than hydroxide. It doesn't mean that one completely goes away, it's just we're changing the balance between them. Versus a neutral solution is when those two values are the same. Right? And if we wanted to go one step further, we could calculate the pH here for this solution. All right, there's not a lot of H plus present, so if you negative log that number, so 5.5 e to the negative 12 molarity, you get 11.26. Does that pH make sense in the context of the question? What did you put into water? A base, and the pH you got is basic. Good. So then you can move on and be confident that your answer is correct. Okay. All right. One more, I guess. Yes. Can we have a negative pH? Let's find out. So you've probably worked with concentrated HCl in lab. Okay. So if you've ever worked with the concentrated HCl, looked at the bottle, it usually has the concentration is a molarity of 12.1 molarity. So how would we calculate the pH? Well, if this is the HCl solution or concentration, we're going to just assume that the H plus concentration is also 12.1 molarity. So to calculate the pH, we're simply going to do negative log of 12.1. And so if you put that into your calculator, so negative log 12.1, yes, you in fact get a negative number, negative 1.03 decimal places, so 0.83. And so yes, this, you can have negative pHs. It just means that your H plus concentration is very, very, very large. And again, I want to remind you the purpose of the pH scale is to represent typically really small numbers. And so that's why when you start to get really, really large concentrations of things, the pH scale isn't as useful anymore because now you start having negative numbers. But what you see is if you do have a negative pH value, it means that your solution is really, really acidic. And you can tell that this is concentrated HCl, so it is going to be very, very acidic, right? So yes, you can have a negative pH. You can also have pHs that are greater than 14 if you have a very, very basic hydroxide concentration as well. All right. Okay, so those are our pH calculations. I want to really reiterate the power of our magic square here. In all of these, you're typically for strong acids and strong bases, you're making an assumption about H plus concentration or OH minus concentration, and most of the time you're trying to make your way back to pH or working your way backwards. I might give you, okay, how much HCl do you have to add in order to get a pH of 4? In that case, you start with pH of 4, calculate how much H plus you need, and figure out like how much product or HCl you need to add. So this magic square is very useful. Do memorize it, how to go to and from pHs and concentrations, and how to traverse the H plus and hydroxides using Kw. All solutions have a little bit of H plus and hydroxide, regardless if it's acidic or basic. It's just their magnitudes are different. All right, so that's the math. We can put our calculators away now. All right, so the rest of the material on chapter midterm 2 is quite conceptual. So we just did these 3 parts of chapter 16. So now we're going to work our way back and look at some of the conceptual aspects of acid-base equilibria. So I'm going to come back to the ways that we can categorize acids and bases. For the most part, we always looked at acids as things that have H+. Bases were things that have OH-. But we're going to categorize acids and bases a little bit more generally, because there's actually a lot more unique type of bases out there that can still donate a hydroxide, make your solution basic, but they just look a little bit weird. So we're going to be using this scale a lot, all right, in terms of acidity and basicity of conjugate bases and acids. We'll look at that in a minute. But first, we're going to look at the 3 ways we can categorize acids and bases. Back in Chem 1210, you basically learned about Arrhenius acids and bases, which basically looked for, does your substance have an H+ present? If it does, then it's an acid. Or does your substance have a OH- present in its formula? That typically meant it's a base. So Arrhenius acid-base theory was very generic. But what we're going to do here is look at 2 other ways to categorize acids and bases that expand our notion of the definition of what makes an acid, what makes a base. And those 2 are Bronsted-Lowry acids and bases, where instead of specifically looking for H+ and OH-, we are actually going to treat a H+ as a proton, right? So if there's anything to memorize, just think Bronsted-Lowry focuses on the protons and how they're moving in a reaction, in an acid-base reaction. While the last one, Lewis acid bases, are the most general of them all, where Lewis acids and bases don't necessarily look at protons, is they actually look at how are electrons moving in a reaction. So what you see here, Bronsted-Lowry acids and bases focus on the protons, but what a Lewis acid base focuses on is how do these electrons move in a reaction. So here is like a generic H+ and OH- is you see, oh, the electrons from the hydroxide is donating into an H+. What you'll see is all these definitions yield the same answer in the end. It's just different ways of thinking about it. Is the H+ moving? Is the electron moving? That's what we're focusing on. Okay, so let's do the first one real quick. Arrhenius acids and bases. All right, so this was back in 1210. This is how we knew HCl was an acid and sodium hydroxide was a base. All right, that Arrhenius acids donate H+, or increase the H+ concentration of a solution. So the giveaway of an acid was if there was an H+ present in it. So like HCl, nitric acid, HF, all of those are acids because they increase the concentration of H+ because there's an H+ present in its formula. So you can see that here, HCl, HF, these are both Arrhenius acids because they produce H+ in those reactions when you put them in water. So the thing about the Arrhenius acids and bases is that it was the most, I guess, crude of all of the definitions. They, all of these definitions and how we categorized substances was purely based on observations. So the idea was if you had this mystery liquid and you wanted to know if H+, if it was an acid, if that substance produced H+ in solution, what Arrhenius did was take these mystery substances and react them with zinc. Right? Because back in Chem 1210, we learned that if you mixed zinc metal with H+, 2 of them, you would get zinc 2+ and H2 gas. So basically, if you put a mystery liquid, mixed it with zinc, the zinc dissolved and bubbles formed, that means H plus was present. But if there wasn't H plus present and you mix those two things, nothing would happen. So that's how he determined whether a substance was an acid or not, is if it would dissolve zinc. That was his definition. It was purely based upon observation, right? Okay, so those are acids. Bases, on the other hand, are substances that increase the concentration of hydroxide in solution. All right, so the most obvious base would be something like sodium hydroxide. You guys use that like every day in lab. And you can clearly see that there's a hydroxide present in that formula. So that's how it's giving that hydroxide. But there's other bases out there that we're going to talk about here extensively in this chapter and the next couple chapters, is bases that don't necessarily look like sodium hydroxide or potassium hydroxide. These are like the hardest kind of bases to identify. They're nitrogen-based bases. So here's another base, but it's a weak base. This is ammonia. Ammonia is a base because it has a lone pair on it, all right? A lone pair of electrons that takes one of the hydrogens from water, all right? So notice that this is an equilibrium. I have that double arrow. And what happens is that you produce an NH4 plus cation, so an ammonium cation and a hydroxide. So notice how this chemical equilibrium also produces a hydroxide, but through a very different mechanism. Notice that in ammonia, there is no OH minus present. Where the OH minus comes from is water, because ammonia steals one of the H pluses from water to make a hydroxide. Ammonia is still a base. It's a weak base, but it's still a base because it produces OH minus in that solution. And so I told you that Arrhenius was very archaic, and he just, made these categorizations via observations. And just like for acids, he just put these mystery liquids, mixed them with magnesium 2+. And what we know from our solubility table is if you mix magnesium 2+ and 2 hydroxides, you get magnesium hydroxide solid. So what he did is just mixed a bunch of mystery liquids, and if a solid was produced, that means that OH minus was present in that solution. It is probably a base. And so that's how he made these categorizations, all right? So we're gonna be looking at a lot of ammonia type looking bases. So definitely practice recognizing weak bases because they're not as obvious as like acids are, because there's no OH minus present in ammonia. All right, those are Arrhenius acids and bases. Okay. All right, Lewis acids, Bronsted-Lowry acids and bases will still come to the same conclusions. Like HCl is still, it's going to be HCl is an Arrhenius acid, it's a Bronsted-Lowry acid, it's a Lewis acid. It's just how we look at it is a little bit different, right? So we want to just change kind of our perspective. Bronsted-Lowry acids and bases focuses on can the substance donate an H plus or can it accept an H plus? That's it. Can it donate or can it accept? That's what we focus on, right? We're not just thinking about H plus and OH minus. No, we're thinking about accepting and donating an H plus. So a Bronsted-Lowry acid is a compound that donates a proton. Bronsted-Lowry acids are proton donors. Because if you look at HCl, does HCl have a proton, an H plus, that it can donate? Yeah, it can. See, it's right there. It's right there. Because when you dissociate, when you put HCl in water, you get an H plus and a Cl minus. That H plus can then be donated and go off and do other things, right? On the other hand, a Bronsted-Lowry base is a substance where a proton is accepted, all right? It's a substance that accepts a proton from something else. So we know that sodium hydroxide is a base, but why is it a Bronsted-Lowry base? Well, we know that when you dissolve sodium hydroxide into solution, you get sodium plus and you get hydroxide minus. We know that this hydroxide is a base. And the reason it's a base is because this hydroxide can, since it has all of these lone pairs, can go on and steal an H plus from somewhere else, all right? And so this hydroxide is accepting, it's accepting an H plus, right? And so that's a Bronsted-Lowry base, something that accepts a proton. So if this is, I guess, very flashcardable, that a Bronsted-Lowry acid is something that donates a proton, while a Bronsted-Lowry base accepts a proton. All right, and definitely how I write reactions, you can see, is this substance accepting or donating a proton? So here's an example. All right, here is nitric acid. It's an acid, so it's a proton what if it's an acid? A proton donor. Yes, so how is it donating a proton? So I've written the same reaction 3 times, one in like the formula form. Here I'm actually showing the chemical bonds and the shapes, and here the chemical bonds again, because what I want you to see is how does this nitric acid donate its proton. So what we see here, here are our reactants, here is our acid, nitric acid. What happens is that nitric acid literally breaks this hydrogen oxygen bond, all right? This bond breaks and this hydrogen goes off to attach to a water molecule, where the new bond is right here. I should highlight it in green. Sure. Right here. There is that new bond. We broke this bond on nitric acid to form a new oxygen-hydrogen bond on this water molecule. So this water molecule took that hydrogen, that proton, off of nitric acid. So nitric acid is donating the proton, but what is water doing? Water is actually taking that H plus, so it is accepting that H plus, that proton. So that means water is acting as the Bronsted-Lowry base. We know that nitric acid is an acid and is a Bronsted-Lowry acid, but in this specific reaction, water is acting as a base because it's accepting that H plus. And so you can see, because that's where the new bond is made, right here between oxygen and hydrogen right here, and we broke this bond in nitric acid, right? So in this example, nitric acid is the Bronsted-Lowry acid, water is actually the Bronsted-Lowry base. Let me focus on the 2 bonds again here. This is the same reaction, just written differently. We broke this bond and we formed that bond right there, right? So here we have water as our Bronsted-Lowry base, because it's accepting that H plus. You can kind of see like the new bond is going to be formed right here. All right, it's accepting an H plus, and then our acid here, nitric acid, is our Bronsted-Lowry acid. It's donating that H plus. All right. And so I want to remind you that just H plus doesn't exist in water. Okay, like just a single H plus floating around. It's always actually attached to a water molecule. It looks like this. This is called hydronium, because you might think, oh, nitric acid splits up into H plus and NO3 minus. This actually doesn't exist. H plus doesn't exist. It's always attached to a water molecule, though chemists we're just lazy and we don't like to write that water molecule out. It actually exists as that hydronium compound. So again, this reaction, HCl breaks up into H plus and Cl minus. Not entirely correct. We actually need to add a water molecule there, but we just don't like to, because we like to be lazy. So the idea here is that when I write H plus, it actually means H3O plus. That's what it actually means. So technically, when we calculate pH, that's not technically correct. H plus doesn't exist. We can't calculate the H plus concentration. It actually should be PH3O plus, or yeah, like instead of pH, it should be PH3O instead. But again, we're lazy. We don't want to write all that. But pH is sufficient as long as you know that H plus doesn't necessarily exist. It's always attached to a water molecule. Okay, so that is Bronsted-Lowry acids and bases. You are focusing on H plus. Notice how I'm saying H plus. H plus is different from hydrogen. It is different. If there's one thing you should keep in your back pocket for organic chemistry next semester for a lot of you is Bronsted-Lowry acid base theory, all right? Okay. Let's do the last one here. All of our inspection of like HCl and sodium hydroxide and Ammonia will always come to the same conclusion, that HCl is an acid, ammonia is a base. But in Lewis acid-base theory, we're focusing on something else. So instead of focusing on how H plus is moving, we're actually going to focus on how are electrons moving. All right, electrons. So here we see kind of our definitions swap a little bit. What we see is that Lewis acids are substances that accept electrons, while bases, Lewis bases on the other hand, donate electrons. Right, so the definitions kind of swap a little bit from Bronsted-Lowry acid-base theory, where we focused on protons moving. Now we're focusing on electrons moving, where now the acids are the electron acceptor, the Lewis base is the electron donor. Let me just show you a really generic acid-base neutralization reaction and help you think about focusing on the electrons. So here's a generic neutralization reaction. H plus, OH minus gives you water. H plus is an acid. Hydroxide is a base. So that means H plus is probably going to be the Lewis acid, OH minus is probably going to be the Lewis base. But why? Think about how the bonds are being formed in this reaction. The bond between H plus and OH minus is formed is actually from the lone pairs around that hydroxide, which I didn't write in the first equation because that's really hard to do in Word. So instead, I had to draw it. All right, draw those lone pairs that exist around that hydroxide. And you can clearly see that those lone pairs on the hydroxide are going to donate into H plus, where these two electrons right here are now in this chemical bond between H and OH, which we know as H2O, right? So see how these two electrons became the bond that donated into H plus to form this new chemical bond to make water, right? Now let's think about that definition of Lewis acids and bases and how electrons are moving. What substance is doing the electron donating? OH minus, yes, that's doing the electron donating. Remember, Lewis bases are electron donors. What substance is accepting those electrons? H plus. H plus is an electron acceptor. It's a Lewis acid, all right? So the great thing about Lewis acid-base theory is now we can actually expand. It's the most general of all of the acid-base theories because an electron acceptor doesn't have to be H plus anymore. It can be something else. As long as the substance is accepting electrons, it can be a Lewis acid. So here is an example. It's a reaction between NH3 and BF3. And I've shown you how the electrons are moving here, that the lone pair on nitrogen is donating into the boron on BF3. So you see that the boron is accepting electrons, so it is the Lewis acid, it's a Lewis acid, while nitrogen and its lone pair is donating into that boron, so it makes it that Lewis base. It's donating its electrons. Right? So typically if you see electrons on something, that is usually a base. It's usually a base. That's why ammonia, because it has that lone pair, is a weak base. And that's typically what we look for. And so you can see that new bond between these two compounds, here's that lone pair, is now in a chemical bond between that nitrogen and boron, all right? So that new bond that is formed is basically the neutralization reaction between this Lewis acid and Lewis base. So the cool thing about Lewis acid-base theory, because we're just inspecting electrons, is that Lewis acids don't necessarily have to be H plus anymore. It can be other things. All right, so that's the Lewis acid-base theory. Okay, so let's do an example. Let's do an example of thinking about our three different definitions, Arrhenius acid base, Bronsted-Lowry acid base, Lewis acid base in two different reactions. So let's identify the Arrhenius acid and base of this first reaction. So remember, Arrhenius acids and bases are purely just looking for H plus and OH minus. What things, when you put them in water, increase those concentrations? Obviously, you see HCl here. This is going to be our Arrhenius acid, HCl, because it has that H plus present, and that makes NaOH our Arrhenius base because it has that OH minus present. All right? While when you think about Bronsted-Lowry acids and bases, you're focusing on how protons are moving within this reaction. So you have to think about the entire reaction in itself. So what you see here is that we're creating a water molecule. It's kind of like double displacement here. So we see that H plus is donating its H plus to hydroxide. And that hydroxide is accepting that H plus from HCl. So that makes HCl the Bronsted-Lowry acid, and it makes sodium hydroxide the Bronsted-Lowry base because that hydroxide is accepting that H plus. While if we want to think about Lewis acids and bases, we want to think about electrons instead. But what you'll see here is that our definitions are still going to be exactly the same. We have H plus and we have OH minus. Only one of these things has electrons to donate. So it's going to make hydroxide, that sodium hydroxide, our Lewis base, and HCl is going to be our Lewis acid because H plus has no electrons to donate. It's only going to accept electrons. So what you see is that all three definitions, right, identify HCl as the acid. You're never going to see them swapped around, all right? It's just how we think about it is differently, either via protons or electrons moving. Okay, so let's do the second one, go through Arrhenius acids and bases, Bronsted-Lowry and Lewis acids and bases. So with this next reaction, really focus on how the bonds are being created and formed. If you look here, this bond between this hydrogen and oxygen is breaking, and you're forming a new bond between nitrogen and hydrogen. So in this example, Arrhenius acid-base theory isn't really useful because it's not as obvious where your H plus and OH minus is coming from. So what we want to actually focus on are Bronsted-Lowry acids and bases and Lewis acids and bases. That might be a little bit easier to help us identify these. So Bronsted-Lowry acids and bases focus on protons. So if you look at this reaction, think about what's happening. This hydrogen is moving over here. So water is doing what to that proton? Is it accepting it or is it donating it, the water molecule? It's donating it. Yeah, so if this water molecule is donating an H plus, look back at the slides, what does it make it? A acid or base? It's an acid, yeah, so it makes water a Bronsted-Lowry acid. And then so what is this ammonia doing then to that proton? It's taking it. Yep, it's accepting it. So that makes the ammonia a what? Bronsted-Lowry base. Yeah, and ammonia is a base, right? Yeah, okay. All right, so we focused on the proton moving. Now let's focus on the electrons instead, but what you'll see is our definitions are still the same, okay? So how is that new bond being formed? Well, that lone pair on ammonia is grabbing that hydrogen to form a new bond, and we're breaking that bond between the hydrogen and water. So nitrogen is donating electrons, so that makes it a Lewis base. And then that makes water with that proton a electron acceptor, so it is a Lewis acid, right? So Bronsted-Lowry and Lewis acid-base theory is a lot more robust. If we can see chemical bonds being formed and broken, it's much more obvious and helpful to us to identify what's going on in a reaction versus Arrhenius acid-base theory is not very great, all right? So what you see here, ammonia is the base in both cases, water is the acid in both cases. It's just how we inspect it is a little bit different. Okay, so a couple more slides. Okay, so let's talk about weak acids and weak bases reacting in water. Remember, weak acids follow a chemical equilibria, K. We'll talk about K later, but weak acids have a Ka expression associated with them. Weak bases have a Kb expression associated with them. The reason weak acids and weak bases are weak is they have these K values associated with them. They don't fully dissociate, but they all follow the same general type of reaction. So here are some very generalized weak acid, weak base reactions. All right, when an acid, regardless if it's a strong acid or weak acid, when an acid is thrown into water, you get H plus and the anion that's left over, right? Regardless of what kind of acid it is. It could be a strong acid or it could be a weak acid. It doesn't matter. They all follow the same general form, right? So there's your acid. It donates its proton, so Brunson-Lowry, and now you're left over with this leftover anion, because remember, everything has to be atom balanced and charged balanced. So what's special about this leftover anion is this is called the conjugate base. HA is the acid you threw into water, but what you get out is not only H plus, but an anion that is its conjugate base, all right? So an example would be like HF. You throw HF into water, that's the acid. F minus is its conjugate base. It's its conjugate, so I removed an H plus from it. But what's neat about this is HF is an acid, F minus is actually a weak. If HF is a weak acid, F minus is actually a weak base also. Yes, and that's where things get complicated. All right, so that's a conjugate base. On the other hand, you throw a base into water when it acts as a base. Yes, you produce hydroxide, but you also form what's called a conjugate acid. So remember, base equations are a little bit more complicated. So this is specifically for weak bases. So this should be a chemical equilibrium arrow, all right, like a reversible arrow. So a general base is you throw a base into water. For a KB expression, you actually have to have a water molecule present. And what's going to happen is that a lone pair on that base is going to steal one of those hydrogens or one of those protons, protonate it. So then what you make is, so it's gaining an H plus here. What you get out is HB plus, so now it's a cation. It gained not just a hydrogen, but also a charge, so HB plus. But then what you're left over is water without an H plus, so a hydroxide. So here you can see, oh yeah, this is clearly a substance that's basic because it produces OH minus in solution. But what's important here is that when a base acts as a base, so steals a proton from water, you make a conjugate acid, so you added an H plus to it. If B is a base, weak base, HB plus is actually a weak acid. That's why we call it a conjugate acid. And we'll come back to that idea in a little bit. Okay, so the tip here is these conjugates always differ by one H plus, right? So if we look here at this reaction, this is ammonia. It's a weak base. When ammonia acts as a base, it makes hydroxide. But the other thing that's in this reaction is NH4+. This is its conjugate acid, right? So ammonia is a base. NH4+ ammonium is its conjugate acid, right? Ammonia is a base. It acts as a weak base. Ammonium, the cation, actually acts as a weak acid. And we'll talk about that in a moment. Okay, so let's make sure that we can write these formulas and identify conjugates of one another. So tell me, what is the conjugate base of all of these things? It might seem like a lot, but it's not that bad. All we want to recognize with a conjugate base is that when a thing acts as an acid, it donates one H plus. Okay, it donates, or what we want to do is remove one H plus from its formula, right? Because I'm asking you, what is the conjugate base of all these things? So all of these are acting as acids, act as acids. So I just want you to tell me, if these things act as an acid, what conjugate base is left over after it acts as an acid. So all we're going to do is remove one H plus. So remember, we're not just removing an H, we're also making sure everything is charge balanced. So we're removing an H plus. So in HCl, you remove an H plus. Yes, you're left over with chlorine, but what's the charge on it? Chloride, so it's Cl minus, because when you add that H plus back, it has to go back to charge neutral. All right, HCN, you throw that into water. It acts as an acid. You are left over with CN minus. CN minus. So I'm just ripping off an H plus. So not just hydrogen, but so don't just write CN. It's specifically CN minus because we're taking off an H plus. All right, H2SO4. Again, we're only going to rip off one H plus, one of them. So we're not going to rip off both. We're just going to rip off one. So what's left over is HSO4, but what's the charge? -1, yeah. All right, but if you note here, okay, we ripped off one hydrogen or one proton off of sulfuric acid, but isn't there still one more? Yeah, so that thing can also, the next thing can also act as an acid. So let's just rip off another proton. What if this substance acts as an acid? The conjugate base we get left over is SO4, but what's the charge? 2 minus, yes. So so sulfuric acid actually has 2 protons it can take off. All right, ammonium. That is an acid. When it acts as an acid, we're still just ripping off an H plus. So what is left over? NH3. Any charge? No charge. No charge. So it's just NH3, right? Water acts as an acid. It's going to donate that H plus. So what's left over is hydroxide. And then finally, if hydronium H3O plus acts as an acid, rip off a hydrogen. So it's H2O, and it's 0 charge because we ripped off a positive cation. So we're just removing one H plus from all of these. So that's making a conjugate base from things that are acting as acids. So obviously we're going to do the opposite. Let's write the conjugate acid of all of these things. So all of these things are acting as what? Acting as bases. Bases accept protons. So we want to actually add back an H plus. But remember, we're not just adding an H, it's an H plus. So you have to be cognizant of the number of hydrogens and the charge. So if chloride acts as a base, which it never will, but if it did, you're going to add that H plus back in and you're going to get HCl. If CN minus acts as a base, it's going to steal an H plus from something and you're going to get HCN back. All right, so we're adding that H plus back in when these things act as bases, and all these things that we're writing are the conjugate acid forms. Ammonia, if it acts as a base, the conjugate acid is going to be NH4 plus. All right, this one's tricky. HSO4 minus. When it acts as a base, remember we gain it, we accept an H plus. So then how many hydrogens are on the resulting conjugate acid? 2, yes. So note here when we're kind of like in the middle, sometimes folks get like confused, like, oh, do I add a proton or remove one? Look at what I'm asking you. I'm asking for the conjugate acid. So this thing has to act as a base and accept a proton. So it's H2SO4, no charge. SO4 2 minus, we're still adding a proton back. Whoops, oh no. Okay, so it's, what is this? HSO4 minus, adding an H plus back on. When hydroxide acts as a base, again, adding an H plus back on, H2O. And then when water acts as a base, again, adding an H plus, H3O plus. All right, so those are all we wrote are the conjugate acid forms of these things acting as bases. Okay. So now I mentioned briefly, you know, acids, the conjugate of a weak acid is actually a weak base. That's why we call them acids conjugate bases. So the extent of how these acids and bases are related to one another are actually inverse, that the stronger your acid, the weaker its conjugate base. The weaker your acid, the stronger your conjugate base. So we need to talk about relative acid strengths, but within the context of acids and their conjugate bases. So here are some acids, and here are those conjugate bases. So HCl, when it acts as an acid, makes the conjugate base chloride minus. When H2SO4 acts as an acid, it makes the conjugate base HSO4 minus because I'm just removing one proton, all right? So this table is showing you both the acid and the conjugate bases on the other side. So what we see here, and I'm going to start filling in this table, is that at the top of this table we have the strongest acids. The strongest acids. So when a really, really strong acid acts as an acid, you get this conjugate base. So if you think about HCl, when you put HCl in water, it's a strong acid, so I use like a total forward arrow. You get H plus and Cl minus. Based upon what we learned about with like reaction arrows, strong acids use the fully forward arrow. Is this reaction reversible? Does it go in reverse? It does not. All right? HCl is an acid only in the forward direction. Chloride minus cannot work its way backwards to act as a base. So what we see is that if a really, really strong acid acts as an acid, its conjugate is nothing. It has no basicity. It's actually a neutral salt, usually. All right? So here what we see is HCl is a really strong acid. Chloride minus, its conjugate base, is actually not a base at all. It is pH neutral. That's what we're getting out here. Right? So what we see here is for all the strong acids, their conjugates are pH neutral. And so what you want to get out of this table is that the stronger the acid, the weaker its conjugate base is in basicity. That's what we're going to kind of look at within, I already wrote that down here, within this table. So HCl is a strong electrolyte or acid. This reaction is not reversible, so that means chloride minus is nothing. It's not a base. Not a base. All right? Because what we're going to see here for weak acids and their conjugates are actually bases. So let's keep looking at this table. All right? So notice, for weak acids and weak bases, here, weak acids and weak bases use a different kind of arrow. They use the equilibrium arrow. So let me ask you, when HF breaks up into H plus and F minus, is this reaction reversible? It is. HF can act as an acid, F minus can go backwards and act as a base. So that's why we see weak acids, all of their conjugates are also weak bases. They act as weak bases, unlike HCl and Cl minus, where HCl is a really strong acid, chloride minus is nothing. It's like the weakest base, it's nothing. But HF, on the other hand, HF is an acid. F minus is also a base. So when we look at this scaling, strongest acids are at the top, and so that means at the top of this list, these are the strongest weak acids. These ones are weaker weak acids. But remember about this idea of, duality, that we have a weak acid, that weak acid also has a conjugate. So the strongest weak acids, if you look at their conjugates, they're actually very poor bases. So here on the base side, you see that base strength actually increases going down. So these guys on the top are actually really bad bases, but on the bottom, these are very strong bases. But if you go back to the conjugates on the other side, these are actually very weak acids, so therefore their conjugates are fairly strong. So here again, this statement, this should be your mantra going into the exam tomorrow, because I will have at least one question on this, is that the weaker the acid, the stronger its conjugate base is in basicity. But this statement is no different than this statement. The stronger the acid, the weaker its conjugate base, or the stronger the acid, the weaker its conjugate base. It's the same exact thing, same statement. So let's see if we can't answer these. Which acid is stronger, HF or H2ClO3? Let's look for these two substances on this graph. So here we have HF, here we have H2CO3. Which one's the stronger acid? HF, because it's higher on the list, yes. All right, so then which one's the stronger base? Technically, do we even need this table to answer this? But let's answer it. So let's look for F minus and HCO3 minus. So we're looking for the stronger base. So I don't want to be looking at the acid section. I want to look at the base section. So we are looking at F minus and HCO3 minus. So you see that, remember, bases increase going down. So that means HCO3 minus is the stronger base. But notice how my answers changed. These two substances, they are conjugates of each other, right? If HF is the stronger acid in this pair, if we compare the conjugates, it's the one with the weaker acid has the stronger conjugate base. So that's why our answer is swapped here, all right? Okay, let's do another one. So those are weak acids. So what we see here at the bottom, we talked about strong acids, weak acids. These substances, hydroxide, hydrogen, methane, have negligible acidity, but if you were to make a conjugate of these would be, you would make really, really, really strong bases. So these substances are strong bases, but their acid forms don't have any acidity. These we don't really look at too often. We're mainly going to be looking at the top part of this table. But I just wanted to complete that table for you, where our strongest bases are down here. Okay, so, oh, dang, that's it. All right, so I want to do a demo, and then I'm going to go into Zoom review where I will do a couple more of these questions that are more exam-like. So let's do that demo, and then we'll take like a 5-minute break and then go right into Zoom review, because this is the last section. That was the last slide before midterm 3 material. So that means the first homework set for chapter 16 is due. It's fairly short. But it'll be due next Monday. So that does mean it's after midterm 2, but I really encourage you to still do it to prepare for the exam. So I wanted to do a demo looking at acids and bases. And the idea, oof, I hope this works. Ow, my head. Okay. I hope this works. Okay. With our intuition, remember, if you put an acid into water, it should become an acid. The pH should go down and it should become acidic, yes. But if you put a base into water, the pH should go up and it should become basic. So I have here a bunch of beakers with indicator in it that change based upon what the pH is. So it's like about green here. It's like a green color. So all of these are pH neutral right now. All right, so it's just like plain water. So I just want to show you via, drastic color change what happens. So this is pH neutral. So what should happen when I add HCl to one of the beakers? The pH should go down. It should become acidic. So let's just see what happens when it becomes acidic. So I'm going to put HCl into this one. Okay. Oh, they didn't give me stuff to stir. All right. So that's the color it is when it is acidic. All right. I added HCl. It's acidic. So let's do the same thing. But this time I'm going to add sodium hydroxide. So what should sodium hydroxide do to the pH? Raise it. So the solution should become basic. All right. So we got neutral, we got acidic, and so now we should see what basic looks like. Okay. Oh, this one's all dumb. Okay. This is what basic looks like. Ooh, see that? Yes, different, right? pH neutral, acidic, basic. So you might be wondering why I have these cans of soda up here. All right. What I wanted to show you is kind of how cool CO2 is. We talked about CO2, CO2 as a gas. All right. Back in chapter 2, the solubility of gases. Right? We love a cold soda on a hot day so much that like if you drink it too fast, it tastes spicy if it's really cold because of all of that dissolved CO2. So CO2 is really cool. When you dissolve it in water, this is what happens. It's actually a chemical equilibrium when you have dissolved CO2 in water. CO2, if it's dissolved in water, like in your soda or whatever, creates an equilibrium with water to make this. What is this? H2CO3. That is an acid. Do you see the H's? Yeah, that's carbonic acid. It's not a strong acid. It's not one of our strong acids. It's a weak acid, all right? So the idea here is, that carbonic acid is acidic. Let's think about what else has CO2 in it. So like sodas have CO2 in it. But what, as humans, mammals, what do we inhale? Oxygen. And what do we exhale? Carbon dioxide. So let's do this demo. I'm not sure if it will work. It didn't work this morning. Let's see if it'll work. So I'm a mammal, so I exhale CO2. So I have a scientific device here called a straw, and I'm going to manually insert CO2 into this beaker, which right now it's neutral. So what do you think CO2 should do to this solution? Okay, we'll see. Okay, what happened to it? It turned acidic, right? Yeah, I had to start with these demos first so you can see. It turned acidic because what did I add to the solution? CO2, which then becomes carbonic acid. Yes, so when we exhale CO2, it becomes slightly acidic, and there you can see. Okay, so I had 2 more demos. Okay, so just to prove it to you that CO2 is acidic, I have a nice LaCroix here to start off the Zoom session. Tons of CO2 in this LaCroix. So what do we think will happen when I put a couple drops of it into this? Should turn acidic, yes. Okay, so let's just check. I want to drink it at the Zoom session, so. What do you think? Yep, that's acidic. Okay, now, remember I told you there's other types of beverages out there that's not just carbonated. There's also nitrogen-based drinks out there. This is a nitro monster because it's not super appropriate for me to bring in a Guinness. So it's actually really hard to find nitro monsters. Yeah, it took me a long time to find it. So this Monster energy drink is made with nitrogen instead of CO2. So is it going to do this equilibrium that we see? Probably not, but let's just see what will happen. So kind of predict what you think will happen when I put a little bit of Monster, this nitrogen-based Monster, into one of these beakers. We'll see what happens. Ugh, I know. When I go to checkout, they're like, do you like these? And I'm like, no. Okay, so what did the nitrogen Monster do? It became acidic. It's acidic. All right, I mentioned before that as humans, we enjoy acidic things. So yes, this drink has nitrogen-based gases in it, but let me read you the other ingredients in it. So it's nitrogenated water, sugar, glucose, and like the 4th ingredient is citric acid. Yes, so it's not necessarily the the lack of CO2 isn't going to be making it basic. There's other acidic things in here, like citric acid, that'll make it acidic. I know I did this the first time, and the students, they got disappointed. They wanted it to be basic or something. Does anyone want this? Yeah, here, you can come get it. You come get it. First time I did this, someone from the balcony in McPherson 1000 came running down to come get it. Okay, but I'm keeping the LaCroix. Okay, so we'll end there. Let's take a 5-minute break, and we'll come back and do the Zoom session. Remember, you don't have to stay. You don't have to stay the whole time. You're free to go whenever. Yeah.